what you and I talk about, the theory and construction of aircraft engines. We're going to lead off by talking about reciprocating engines, you know, these with pistons that fly all around and shake and rattle. We'll get into turbines later on. All right, let's talk about the 5 events in a 4-stroke cycle engine. Now, wait a minute. What in Sam Hill is a 4-stroke cycle engine? It's just a 4-cycle engine. That's the FAA's fancy terminology for a 4-cycle engine. They call it a 4-stroke cycle engine. And yes, you heard me right. I said, what are the 5 events in a 4-stroke cycle engine? Well, here's the way the FAA does it. We all know how an engine works. The intake valve opens, the piston goes down, it sucks in the fuel-air mixture, and that's called the intake stroke. And then both valves close, the piston goes back up and squeezes the fuel-air mixture. That's called the compression stroke. And here's the 5th event. The spark plug fires, you have ignition. And with both valves closed, the fuel-air mixture burns and expands, shoving the piston back down, and that's called the power stroke. And then the exhaust valve opens, the piston goes up and shoves out the exhaust out the exhaust system, and that's called the exhaust stroke. And so the 5 events in a 4-stroke cycle engine are intake, compression, ignition, power, and exhaust. Now, I said that in class one time, and some guy said to me, "Hold it, wait a minute, that's way too doggone complicated." I said, "Complicated? What are you talking about? What's so complicated?" All I said is, any internal combustion engine is simply a matter of intake, compression, ignition, power, and exhaust. This is way too complicated. All right, what's less complicated? I said. He says, "Well, everybody ought to know." He says, "Especially you ought to know. Any internal combustion engine is simply a matter of suck, squeeze, fire, bang, and blow." All right, you can make out of that whatever you want. That is not official FAA terminology, but it does help me to remember it. But as far as the FAA is concerned, any internal combustion engine is simply a matter of intake, compression, fire, or ignition, power, and exhaust. All right. Now, they ask you some questions about a 4-stroke cycle engine, and they're going to say, on the compression stroke, would the intake valve be open or closed? Well, if you expect to get any compression at all, it's got to be closed. So the intake valve closes on the compression stroke. And they're going to say, all right, let's assume the exhaust valve of a 4-stroke engine is closed, or they call it a 4-stroke cycle engine is closed, and the intake valve is just closing. What stroke are you on? Well, once again, if both valves are closed, that's the compression stroke there, because the intake valve is just closing, and it does that on the compression stroke. Now, here's a couple concepts that are really going to be useful to you to understand some questions later on for the written exam. These 2 concepts, you probably already know them, by the way, are top dead center and bottom dead center. And they're going to be helpful in determining valve overlap and setting timing and answering questions on a test more than anything else. All right, let's take a look at it. Top dead center is when the piston has gone on its upward path and stops and reverses itself and starts back down again. And top dead center is when the piston reverses itself right there. And by the way, it's also when the piston is furthest away from the crankshaft, because the piston is going up away from the crankshaft at that point. What's bottom dead center? Well, it's when the piston is going down, gets to the bottom of its stroke, and then reverses itself. And at that point, the piston is as closest to the crankshaft that it's going to be. That is top dead center and bottom dead center. We're going to talk about those concepts later on. Now, another concept we want to talk about is valve overlap. Now, when I explained intake, compression, power, and exhaust, I implied that these valves open and close at top dead center and bottom dead center, but they don't. In order to help the engine breathe a little better, scavenge the exhaust out of the engine and so on, these valves open at slightly off the top and bottom dead center. For instance, let's take a look at it. First of all, at the end of the exhaust stroke, very often you'll find that the intake valve, when the piston is going back up on the exhaust stroke, the intake valve will open 15 degrees before top center. Now, the reason for that is, as the new intake comes into the engine, the fuel-air mixture comes into the engine, it helps shove out the burnt mixture out the exhaust system. So the intake valve actually opens at the end of the exhaust stroke, 15 degrees before top dead center. Now, both valves are open for that 15 degrees, and then the exhaust valve also is open until the piston starts back down 15 degrees after top dead center, because you're still having some of the intake come in and shove the exhaust back out. So there's actually 30 degrees of valve overlap, and it's on as you start you finish the exhaust stroke, the piston's going up, and start the intake stroke. During that time period, both valves are open for 30 degrees, and that's called valve overlap.
Now, they're going to ask you a question about this on the test, and the question they're going to ask you is, why do you have this valve overlap? Why do you have two valves open at the same time? And what is the importance in proper valve timing? Why is that so important? And there's actually two reasons you have valve overlap and two reasons proper valve timing is so important. And these two reasons is that these things help obtain best volumetric efficiency. You might say, well, what is volumetric efficiency? Well, that's the ratio of the charge you're putting into the cylinder to the displacement of the cylinder. And if you're getting a lot of charge in the cylinder, it means you have very good volumetric efficiency. And the other reason proper valve timing and overlap is important is that you get lower cylinder operating temperatures. Now, these are the correct answers to this question on a test. They also give you a couple false answers that don't make sense. They're actually correct answers, but they're not complete answers. For instance, one false answer they give you is that you want to achieve the best possible fuel air charge, and that's the reason you have proper valve timing and overlap. Well, getting the best charge is one element in volumetric efficiency, and getting the best charge in is actually a function of how long you have the intake valve open. And that's not the correct answer. The correct answer is obtain best volumetric efficiency. Another answer they give you that's not totally complete is that the reason you have valve overlap is you get better scavenging of exhaust gas. Well, the reason you get good scavenging of exhaust gas, the most important thing is opening the exhaust valve before you get to bottom dead center, and that's just lets the exhaust start out early on the power stroke, and that's how you get good exhaust gas scavenging. But that's not the correct answer to the test. The correct answer on the test is the reason proper valve timing and overlap is so important is so that you can obtain best volumetric efficiency and lower cylinder operating temperatures. And in this particular case, it's important to know these two answers word for word. Now, they're going to say, all right, what would happen if the intake valve would open too early? Instead of at 15 degrees before top center on the exhaust stroke, let's assume it opened, say, 30 degrees. What would happen? Well, you could have what they call backfiring through the intake, because if this intake valve opens too early when the piston's going up on the exhaust, you're going to have a lot of hot exhaust go into the intake, and that can ignite the intake mixture, and you have a backfire through the intake of the engine. So backfiring would occur, this is FAA words I'm using here, if the intake valve opens too early, because the exhaust gases would flow into the intake manifold and ignite the incoming fuel air mixture. So valve overlap promotes better scavenging and cooling characteristics of the engine. By the way, don't try and memorize these valve overlap numbers. That varies. Sometimes the exhaust valve closes some 10, maybe 15 degrees after top dead center. Once again, it varies. So let's you and I take a look at how the valves might operate on all four strokes of a reciprocating engine. And here's a typical engine here. And we're starting off with the intake stroke, and of course the piston is going down. Well, on the intake stroke, the exhaust valve doesn't close until about 10 degrees after top dead center, because exhaust is still going out, even though the piston's starting back down. So the exhaust valve closes on the intake stroke 10 degrees after top dead center. Now, we've got the piston going down, the intake coming in the engine, and on the compression stroke, the intake valve stays open and doesn't close until 45 degrees above bottom dead center, or after bottom dead center. Now, the reason for that is, even though the piston's starting back up, the intake valve is still open because some of the fuel air mixture is still rushing into this cylinder. Okay, now, both valves close at 45 degrees above bottom dead center. Finally, the intake valve closes. Now you compress the fuel air mixture as the piston goes up, and of course you have ignition, the spark plug fires, the fuel air mixture burns and expands, shoving the piston down, and you think of both valves being closed for the entire power stroke, but they're not, because at 70 degrees before bottom dead center, the exhaust valve opens and the fuel air burnt mixture starts going out the exhaust system right at this time, because in the first part of the travel, almost all of the energy has been taken out of that power stroke at that point. And so now we're using the last little bit to help the exhaust go out, to help cool the engine finally. And now you have the piston going back up on the exhaust stroke, and about 15 degrees before top dead center, the intake valve opens, as you remember, to help scavenge the engine, to shove out some of the, to help have the intake come in and still replace some of the exhaust there. So here's how the valves might operate in this particular case. Now, here's the question they're going to ask you about this on the FAA written exam. They're going to say, given this particular situation now, how many degrees of crankshaft rotation are both
valves seated this time. Now, earlier we talked about valves being open, but now we're talking about how many degrees of crankshaft rotation are both valves seated. Well, let's see if you and I can figure it out. Let's take a look at the numbers. First of all, we think of, it's not correct, but we think of during the power and compression strokes, both valves are closed. So let's start off that way. Let's assume that were the case, and then we'll make some deductions and change it from there. But think of on the power stroke, both valves being closed. That's 180 degrees of rotation of the crankshaft. And on the compression stroke, both valves being closed. That's 180 degrees also. So on the compression and power strokes is 360 degrees. But we know that both valves aren't closed. For instance, the intake valve closes 45 degrees after bottom dead center, not at bottom dead center. So you can subtract 45 degrees of crankshaft rotation there. And we know that the exhaust valve opens on the power stroke 70 degrees before bottom dead center. So instead of, on those two strokes, instead of both valves being closed for 360 degrees, they are closed for 360 degrees minus 45 degrees minus 70 degrees, and both valves are closed for 245 degrees. Now, those are the kinds of questions they're going to ask you about valve operation and also about valve overlap. You do not have to memorize these numbers. All you have to do is, given these numbers, figure out that answer, and that's all there is to it right there. All right. Now, as you know, the pistons in an engine don't fire in 1, 2, 3, 4, 5, 6, 7, 8, 9 order. So let's assume you had a 9-cylinder engine. They don't fire in 1, 2, 3, 4, 5, 6, 7, 8, 9 order. What they do is they fire in a firing order that skips around the engine a little bit. Now the question is, why do you have a firing order that does that? And the reason is that helps eliminate vibration and helps balance the engine. They're going to ask you particularly, here's the way the question goes on the FA1 exam, what is the firing order on an inline V-type or an opposed engine designed to do? And we're talking about a reciprocating engine. And the answer is the firing order is designed to eliminate vibration to the extent that's possible and to provide for balance of the engine. Now, we're going to solve a problem in just a minute. And in order to solve that problem, you need to know the firing order in a 9-cylinder radial engine. Now, the engines are numbered so that the number 1 cylinder is at the top, and as you're sitting in the aircraft, 2, 3, 4, 5 are clockwise as you go around. Now, that's how the cylinders are numbered. How do they fire? What's the firing order? Let's you and I take a look at the firing order in a 9-cylinder radial engine, and it's really pretty easy. What you do is, first of all of the odd cylinders fire, 1, 3, 5, 7, 9. Then you go back and all the even cylinders fire, 2, 4, 6, 8. And that's the firing order in a 9-cylinder engine. You guys got that? Nothing to it. 1, 2, 3, 4, 1, 3, 5, 7, 9, 2, 4, 6, 8. Nothing to it. All right, now here's the question you need to know. They say, all right, super mechanic, let's assume that you're using a differential pressure to test the compression on an engine. The pressure, you're doing a compression test on an engine. And you're using the number 3 cylinder, and you've rotated the engine, first of all, at top dead center stroke for the number 1 cylinder. So you've got a top dead center compression stroke, number 1 cylinder. Now you rotate the engine another 260 degrees. You have the spark plug off the number 3 cylinder. And when you try and check compression, you get no pressure at all. It won't hold pressure. The question is this normal? Well, first of all, you need to know where the number 3 cylinder is in the firing order, and the answer is it fires 1, then 3. So it's the second cylinder to fire. First one after number 1. All right, you got that. Now let me ask you a question. How many degrees of rotation does the crankshaft have to go before all 9 cylinders of a 9-cylinder engine fire? And the answer is 720 degrees. Because to get all 4 strokes in on all 9 cylinders, you have to rotate the engine 2 times around. Once is 360, another time makes 720. All right, now let me ask you another question. Then if you have 9 cylinders that fire in 720 degrees, then how many degrees in between each cylinder firing? Well, let you and I take a look at that. How many degrees? Well, 720 divided by 9, or 80 degrees. Now, here's the question I want to ask you. That to check compression in this number 3 cylinder, you've rotated the engine 260 degrees. So as far as that particular cylinder is concerned, where is it in its cycle? And the answer is 260 minus 80. Because number 1 is up here, number 3 is over here, so number 3 is 80 degrees after number 1, so you take 260 minus 80, and when you're checking the compression on number 3 at this particular point, it's at the 180 degree point. Now, what is the 180 degree point? The piston is at the bottom of the cylinder on the power stroke. Well, at the bottom of the cylinder or on the power stroke, what is the position of the exhaust valve? And the answer is the exhaust valve is open because the exhaust valve normally opens somewhere around 70 degrees before bottom dead center. You already knew that, didn't you? So if you don't get any compression in this cylinder, is that normal? And the answer is absolutely normal. It'd be very hard to get compression because the exhaust valve is open. These are the kinds of questions they're going to ask you about this, and it's simply a little bit of mathematics. You need to know that the number 3 cylinder is the second one in a firing order in a 9-cylinder engine. Therefore, it's 80 degrees behind the number 1 cylinder. If you rotated the engine 260 degrees, that number 3 cylinder is at the 180 degree point, and you know that's the bottom of the power stroke. See, nothing to it. So, how are engines timed? Well, they're also timed the ignition as well. And the whole idea is if the ignition and valves are adjusted properly and the fuel-air ratio is proper, the combustion process actually should be completed just after top dead center at the beginning of the power stroke. In order for that to happen, the fuel-air mixture is generally ignited before the piston gets to the top of the compression stroke. How much before? Generally about 28 degrees. The fuel-air mixture on a compression stroke is normally ignited 28 degrees before top dead center. So let's assume that the ignition occurs on an engine somewhere at around 28 degrees before top dead center on a certain 4-stroke engine. And let's assume that the intake valve opens. Now let's assume that you have compression going up 28 degrees before top dead center, the spark plug fires, fuel-air mixture burns, piston continues up, and then at top dead center, the piston reverses itself, and now you have the power stroke, okay? You complete the power stroke, and then you have the exhaust stroke. And let's assume on the exhaust stroke, the intake valve opens, as you know it does, 15 degrees before top center. Let's assume that's the case. Now, the question they're going to ask you about this is how many degrees will this crankshaft travel after ignition before the piston comes back around again and the intake valve opens on the exhaust stroke, or before the intake valve opens again. Let's you and I take a look at the numbers. First of all, we have the compression stroke, and before you get to top center, the ignition occurs 28 degrees before top center. So you have that 28 degrees first, and then you get to top dead center. And then you start the power stroke. You have 180 degrees of power stroke, and you would have 180 degrees of exhaust stroke. So you have 360 degrees there, but hold the phone. The exhaust stroke has the intake valve opening 15 degrees before top center. So you'd have to subtract that 15 degrees, and the answer to the question is 373 degrees. Now, what was the question? The question is, how many degrees does the crankshaft travel from the time you have ignition before the intake valve opens again? And the answer is 28 degrees plus 360 minus 15, or 373 degrees. You have to have a pretty good idea of how a piston engine works to answer these, but once you have that, you've got it nailed. All right, now, let's take a look at another question. They're going to say, all right, super mechanic, you have an engine with a stroke of 6 inches. That's how far the piston travels in one direction, either up or down. And that engine is operated at 2,000 RPM. Now, the question is, when will the piston be moving at its maximum speed inside the cylinder? And the answer is, there's a lot of smoke in this question. It doesn't matter what the stroke is. It doesn't matter what RPM the engine's operated at. The piston inside the cylinder is always moving at maximum speed when the crankshaft is 90 degrees, like so. And what happens at that particular point, of course, is the piston is moving as fastest at maximum velocity, and the connecting rod and the crank or throw crank are at right angles. And when that's the case, the piston is going the fastest because the radius has the piston moving its greatest speed at that particular point. All right, now here's a question they ask you on the FAA written exam. They say, what is the total piston displacement of an engine, and how do you figure it? Well, the way you figure out the displacement of an engine is you take this little circle at the top of the cylinder and find the area of it and multiply it times the stroke. And that will tell you the displacement of one particular cylinder. Then all you have to do is multiply that times the number of cylinders. All right, how do you find the area of the circle made by the top of the piston? And the answer is the area of a circle is pi r squared. Pi, we know, it's 3.14. That's all you need to know about that. You don't need to know the number of the rest of all of those digits after the decimal point. It's 3.14. The radius is whatever the radius of the piston is, and it's going to be half of the bore of the piston. So pi times the radius squared times h, which is the stroke, times the number of cylinders. Now, pi r squared tells you the displacement of one cylinder. Multiply that times the number of cylinders, and that tells you the entire displacement of an engine. But you and I put some numbers in this. Let's assume you have a 9-cylinder engine, and let's assume that that engine has a bore of 5.5 inches. Now, wait a minute. We don't need the bore, we need the radius. So the bore is the total diameter of the piston. We want half of that. So take that 5.5 divided by 2. When you get to the answer of that, multiply it times itself, and that's the square. That's radius squared right there. If you take 5.5 divided by 2 and multiply it by itself, that's radius squared. All right, now, the total displacement is what we want to know. It's a 9-cylinder engine, has a bore of 5.5, and let's assume it has a stroke of 6 inches. Let's assume they give you all of that. Well, what you would do is take the pi, 3.14, take the diameter of the piston, which is the bore, and divide it by 2, and then multiply that answer by itself, and that gives you the radius squared. Multiply it times 6, because that is the stroke of the engine. Multiply that times 9, because it has 9 cylinders in the engine, and you have figured out the displacement of that particular engine. All right, in this case, if you use your electronic calculator and do all this, you find out it's 1,283 cubic inches. And that's about an average displacement for a 9-cylinder engine. How about that? All right, now let's talk about another concept they want you to know about, and that is the compression ratio of a cylinder. How do you find the compression ratio of a cylinder? The answer is you take the total volume of the cylinder when the piston is at the bottom, and now the cylinder has a big volume to it, and you divide that by the volume of the cylinder when the piston's at the top of the cylinder, and that gives you the compression ratio of that particular engine. Let you and I figure out the compression ratio of an engine. First of all, let's assume when the cylinder's at the bottom, the volume is 70, and let's assume when the cylinder's at the top, the volume is 10. How do you find the compression ratio? All you have to do is divide. What's the compression ratio of this engine? 7:1. It's written 7:1. Fantastic. All right, now, why do you have an engine with lots of cylinders in it? The P-51 Mustang had that beautiful Merlin engine, sounds like silk, has 12 cylinders. Why so many cylinders? Well, with a greater number of cylinders, the smoothness of operation of an engine increases. And why? And the reason is because the power impulses are spaced closer together. I'm beginning to learn to talk just like the FAA here. All right. And what enhances engine operating flexibility, and what is engine, what they call operational flexibility? And the answer is engine operational flexibility is the ability of the engine to run smoothly and give desired performance at all speeds, and of course timing has a great deal to do with that. How many times does a crankshaft have to rotate for each cylinder to be fired in an engine? And the answer is if it's what the FAA calls a 4-stroke cycle engine, the crankshaft must make 2 complete rotations for each cylinder to fire. All right, so the question is, if you have a 4-stroke cycle engine and that engine is to be fired 200 times a minute, how many times a minute must the crankshaft rotate? The answer would be 400 times a minute. Now let's take a good look at a crankshaft, and one of the things the FAA wants you to know about crankshafts is that there's movable counterweights in here. These are weights that can move around, called movable counterweights. They're going to ask you on a test, what are these movable counterweights used for? Well, the answer is these movable counterweights are used to reduce torsional vibrations. That's twisting vibrations on the crankshaft. If you put a big rod on the table and a great big flywheel at each end, you could get these flywheels going back and forth like this, and that would be torsional vibration. Well, that's a bad deal in a crankshaft. It's a type of dynamic vibration. It says not dynamic vibrations. It's not all dynamic vibrations. They're looking for torsional vibrations. That is a type of dynamic vibrations. But the thing you need to remember is the purpose of these movable counterweights is to reduce torsional vibrations, not just dynamic vibrations, because they're specifically looking for torsional vibrations. Now let you and I talk about cylinders, and here is a cylinder right here inside an engine like so. And by the way, the FAA wants you to know sometimes you have a choke or taper ground cylinder, and the whole cylinder itself is bored with a slight taper or choke, kind of like a shotgun can be in sometimes. And the end of the bore nearest the head is smaller than the skirt. Now this is the skirt down here, and this is the end of the bore nearest the head inside there. And what you need to know is the reason it is smaller is to allow for expansion at greater operating temperatures near the head. And when you get done, you'll have almost a straight cylinder, and that bore won't go away when the engine gets hot. So when the engine is hot, the narrower taper here near the cylinder head expands, and therefore it gets to become a straight cylinder rather than a tapered cylinder at that point when the engine is hot. That's why they grind cylinders sometimes with what is called a choked or tapered ground. All right, now let's take a look at the cylinder walls. And the cylinder walls of an engine get the tremendous amount of wear, and we're going to ask you, where do they get the greatest amount of wear? And the cylinder walls get the greatest amount of wear near the top of the cylinder, and that's where the temperatures and the pressures are the greatest, near the top of the cylinder. So the greatest wear on the cylinder is near the top. These are FA test questions coming at you hard and fast here. Well, what do you do about the wear that these cylinders get? Sometimes they get a tremendous amount of wear. Well, one of the things you can do is harden the cylinders with a process called nitriding. So nitriding is a process of forging a steel alloy cylinder barrel with the inner surface hardened to resist wear of the piston and piston rings which bear against it. So they've hardened this inner surface here. And the hardening is usually done by exposing the steel to ammonia or cyanide gas while the steel is very hot. And the steel soaks up the nitrogen from the gas, which forms iron nitrides on the exposed surface, and it makes that harder. Now, as you might guess, there's an FA test question about this, and they want you to know simply that the inside of some cylinder barrels is hardened by nitriding. That's that process we just described right there. Now let's talk about the exhaust port valve of an air-cooled engine. They're going to say, why is it that the exhaust valve very often has more fins around it? That area around that part of the cylinder has more fins per square inch than the rest of it. And the answer is that's where most of the heat is going out, that exhaust. And so the exhaust part valve is the one that has the greatest fin area per square inch because that's where the greatest amount of heat is. All right, now they're going to ask you, let's assume that the pilot is operating this engine and he makes a change in the manifold pressure. Let's assume he increases the manifold pressure by putting the throttle forward. That's one way to do that. Would that have an effect on the mean effective cylinder pressure, mean effective cylinder pressure? Well, it's a trick question. They really want to know, do you know what mean effective cylinder pressure is? And the answer is mean effective cylinder pressure is the average pressure in the cylinder on the power stroke. When the piston is coming down on the power stroke, it's the pressure in the cylinder. Would changing the manifold pressure have any effect on the mean effective cylinder pressure? And the answer is certainly it would. You're burning more fuel-air mixture and you're going to have a greater mean effective cylinder pressure. Okay, now let's take a look at the factors used in establishing the maximum compression ratio of an aircraft engine. And they're saying, okay, super mechanic, today you are an engineer and you're going to design an engine and you want to determine the maximum compression ratio limitations of that aircraft engine. What factors, Mr. Engineer, will you consider? Well, one of the things you consider is the detonation characteristics of the fuel used. If you're going to a remote area of the world where you cannot get high-octane fuel, you could not have as high a cylinder compression ratio because the fuel would detonate and the engine wouldn't work. So you have to figure out the fuel you're going to use, and that's one of the factors you'd use in determining the compression ratio of the engine you're designing. Also, you'd have to take the design limitations of the engine. Here I think we're talking about what materials is this engine made out of, what kind of pressures can the engine itself take, and finally the degree of supercharging is going to determine the compression ratio that the engine has. When you supercharge a lot, you're more likely to have detonation. So if you are going to supercharge a lot, you probably have smaller compression ratios in the engine. So these are the factors, Mr. Engineer, you need to consider when you're designing an aircraft engine in regard to compression ratio limitations of that engine. Now, why they ask a question like that? I don't know. Maybe you are going to design some engines, that's all. All right, now let's you and I talk about pistons and full floating pins in a piston. They're going to say, all right, here's a piston, here's a rod. What is a full floating pin? Well, first of all, of course, the pin is a connecting place between the rod and the piston itself. And if it's a full floating pin, it means that you can have motion between the pin and the piston itself, and the connecting rod. So the pin can rotate clear around, have motion in between the piston itself and the connecting rod. And if it can have motion between both of those two, it's called a full floating piston pin. All right, now they're also going to ask the question, why is it sometimes the undersides of the pistons are fin? Now, in this particular case, it's not, but the answer is to provide for greater heat transfer to the engine oil. So if you see fins here, it gives greater heat transfer to the engine oil. Now, let you and I talk about bearings. Now, a bearing is any surface that supports or is supported by another surface, and bearings, of course, are designed to reduce friction of moving parts. They're designed to take loads. Kinds of loads are thrust loads, which are along the axis of the bearing, and radial loads, which are out from the center of the bearing, or a combination of both. Now, types of bearings include plain bearings, and plain bearings are designed to take radial loads and are used generally for connecting rods, crankshafts, and camshafts in lower power engines. And here's a good example of a plain bearing over here. These are all plain bearings over here. Next is a roller bearing. Now, they're also known as anti-friction bearings. They can be adapted to either radial or thrust loads, and here's a good example right here of a roller bearing. Finally, ball bearings provide less friction than any other type. A ball bearing consists of an inner race, like so, an outer race, and a set of polished steel balls, and a ball retainer, which keeps these balls from contacting one another, and that's a ball bearing. By the way, in high-powered reciprocating aircraft engines, there is less rolling friction when ball bearings are used than when roller bearings or any other type are employed. So the ball bearings have less rolling friction than any other type of bearing. Now, we talked earlier about a thrust bearing. That's one that's designed especially for thrust loads, and it's made with exceptionally deep grooves for the ball races. And bearings designed to resist thrust in a particular direction will have a heavier race design on the side which takes the thrust. And a deep groove ball bearing, or deep groove ball, is a characteristic of a thrust bearing used in most radial engines. Now, they ask you some questions about radial engines. One of them is, the master rod bearing in a radial engine is least likely to be what kind of bearing? Well, it's least likely to be a roller or a ball bearing, and it's most likely to be a plain bearing. How much less likely? Well, it's less likely than a rocker arm bearing or a crankshaft main bearing or a generator armature bearing. Those aren't as likely to be plain bearings as is the master rod bearing in a radial engine. All right, now let's talk about another thing having to do with radial engines. They say if you have a radial engine and you increase the manifold pressure but maintain a constant RPM, will that increase or decrease the load? And this is FAA words off the exact test here. So will it increase or decrease on the load on the bearing between the crankshaft and the master rod bearing in a single row radial engine? And the answer is, when you increase the manifold pressure in an engine, particularly if you keep a constant RPM, you increase the load on almost every bearing in the engine. Now let's take a look at how the valves operate in an engine, and to do that we'll take a look at this old radial engine here. That's what we have, and notice we have a great big cam with lobes on it. The lobes lift this cam follower, which then the whole mechanism pushes this valve lifter up. And then we have a push rod, and then you have a rocker arm, and then the valve goes down and opens, and that's how the whole thing works. Now, they're going to ask you a lot of questions about hydraulic valve lifters and mechanical valve lifters, and this is the valve lifter. It's also called a tappet, and it's the link in between the cam itself and the push rod up here. And in the old engines, or in older engines, these used to be mechanical, and when the engine got hot and cold, the clearances would change, so you had to always adjust the clearance for when the engine was running hot, and you could adjust the valves. And that was called adjusting the valves, and you were adjusting the clearance in between this tappet or valve lifter and the push rod. But today, on more modern engines, we use hydraulic valve lifters or hydraulic tappets, and you get rid of that problem. Let's take a look at how a hydraulic valve lifter works. Here we have a hydraulic valve lifter, and just to orient you here, here's the cam. The lobe comes around and pushes against the tappet, and the tappet shoves over in this direction, and here's the push rod and pushes the push rod over. Now, the deal on a hydraulic valve lifter is that it fills with hydraulic fluid. There's a spring and a check valve, and the whole mechanism works such that the hydraulic fluid we're talking about here is engine oil in this particular case, by the way, but the whole mechanism works such that there is no play here. Oil always fills up the space where there would be play, and so therefore you have no play back and forth. There is no clearance on a hydraulic valve lifter, and therefore this is called a zero
lash lifter. Now they're going to ask you about these zero lash lifters. That's a hydraulic valve lifter, or a tappet they call it. And so they're going to ask you during normal operation of an overhead valve engine using a hydraulic valve lifter, how much clearance would be in the valve operating mechanism? And the answer is there is no clearance. It should not exceed 0.000, none at all, after you've reached the minimum inlet oil temperature and cylinder head temperatures for takeoff. So there'd be no clearance at all. Now, let's assume that this piston assembly inside this hydraulic lifter has gone all the way to one extreme. Obviously, you need to adjust the clearance, but you can't do it. How do you do it? Well, the only way you can adjust the clearance in this particular case is simply change the push rod with push rod replacement, because you cannot adjust the hydraulic valve lifter. If things aren't working out right, you need to change your clearances, you replace your push rods. Just get a different length push rod. Now let's take a look at the valve assembly one more time. And one of the things we want to take a look at is the springs. And sometimes when you look at the springs in a valve assembly, you'll notice that each valve sometimes has more than one spring, maybe two or more springs. Why would the valve have two or more springs? And the answer is to eliminate valve spring surge. Now, when you have a spring that can oscillate, it'll have a resonant frequency. And sometimes the engine can run at the resonant frequency of that spring. And in that case, the spring will float, the valve will float, it will not work properly. And to eliminate that, you put in two or more springs, each of the springs having a different resonant frequency, and you hope, therefore, that you eliminate valve spring surge. Now, sometimes these valves in aviation engines are not solid valves. They are filled with sodium. This is particularly true on exhaust valves. Why would that be? And the answer is to dissipate heat well, because exhaust valves particularly have a tremendous amount of heat going by them. You need to be cooled down, and they fill these valves, exhaust valves, with sodium to dissipate heat well. Now, let's assume that you are flying in an airplane that has an engine with valves like this. Most of them do if you're flying a piston engine aircraft, and you're having a bad day. Let's talk about what could happen if you're having a bad day. Well, there's a lot of wear and tear with this rocker arm pushing against the end of the valve here, and let's assume the end of the valve stem breaks off. Now, if you're having a bad day, what could happen is the valve could then fall inside the cylinder, the piston's going up and down, the valve beats a hole in the piston, and you lose your engine oil and the engine quits, and that could cause an accident. You've had a bad day. Now, if you want to eliminate or minimize the chance of that happening, what you can do is install what is known as a little safety circlet up here near the top of the valve spring, and that safety circlet will prevent the valve from falling into the combustion chamber should the tip of the valve break off here, and thereby preventing that scenario from happening. So that is what is known for obvious reasons as a safety circlet. All right, let's you and I talk about propellers and propeller reduction gears. First of all, the propeller type certificate data sheets contain a table that lists the engines to which a given propeller is adaptable, translating that into English. If you want to find out if you can put a certain propeller on a certain engine, you go to the propeller type certificate data sheets. That's where you go, type certificate data sheets. All right, now let's talk about gear reduction of propellers, propeller reduction gears, and what's the purpose? Well, here is an example of a radial engine that has a propeller reduction gear, and it operates the propeller at a much lower RPM than it does the engine. Now, the reason for that is to allow the engine to have a higher RPM, it gets more power, to allow the propeller to operate at a lower RPM so that it's more efficient. Actually, it's much more efficient aerodynamically for propellers to operate at slower speeds generally than engines. So you have a propeller reduction gear to allow that to happen. Now, here's a real-life example of a propeller reduction gear. And once again, the whole idea is you're trying to reduce propeller RPM while keeping your engine RPM up. And so you're talking about how much reduction there is. Now, they're going to ask you a question about this on the test. They're going to give you several gear ratios. They're going to say which one gives you the highest engine RPM. Well, the whole idea of gear reduction ratios is to reduce the propeller RPM. So they're going to ask which one gives you the highest propeller RPM. It's the one with the least reduction. Here are the ratios. They give you 16 to 7, 20 to 9, and 3 to 2. To answer this question, all you have to do is take out your electronic calculator and divide 16 by 7, 20 by 9, and 3 by 2, and you get reduction ratios of 2.29, 2.22, and 1.5. Now remember, the question was, which one will give you the highest propeller RPM? It's the one with the least reduction ratio, and it comes out to 1.5 in this case. All right, now let's take a look at the next thing, and that is, how do you attach engines to airframes? And the way you do it is with suspension. A couple concepts we need to talk about. First of all, dynamic suspension is putting rubber mounts on the engine, or synthetic rubber mounts. And let's take a look at some synthetic rubber mounts, and these are called dynamic suspension. And that just eliminates vibration. That's the whole idea, just to get vibration from it. The next thing we want to talk about is dynafocal mounts. Now, dynafocal mounts are designed so that you take the stress axes and extend them, and where they intersect will be at the center of gravity of the engine. And basically what it means is you're essentially supporting the engine about its center of gravity, or the center of its vibrating mass. They call that the focal point, and that gives a much smoother operation. So the FAA will ask you a question about this. First of all, they're going to say, what is the purpose of dynamic suspension? And the answer is to isolate normal power plant vibrations from the aircraft structure. Now, let's wrap up piston engines by talking about a few miscellaneous things the FAA wants you to know about. As a mechanic, they figure you ought to know standard sea level pressure in inches of mercury is 29.92. By the way, you do not need to worry about millibars of mercury, millibars of pressure. It's 29.92 inches of mercury. As a mechanic, the FAA figures you ought to know about standard sea level temperature. It is 59 degrees Fahrenheit. Once again, you don't need to worry about the Celsius. It's 59 degrees Fahrenheit. That's what you need to worry about right there, standard sea level temperature. Now, if you want to install this engine on an airplane with a standard airworthiness certificate, what do you have to have? And the FAA says each power plant must have what is known as a type certificate. So if you want to install an engine on an aircraft with a standard airworthiness certificate, what's the engine have to have? The answer is a type certificate. Now, they're going to ask you on the test what critical altitude is. Well, critical altitude is the highest altitude at which any engine, including a turbocharged engine, will maintain sea level pressure in the manifold. In that case, it can get sea level rated power. Now, on a normally aspirated engine, that critical altitude would be sea level. As soon as you leave sea level, the engine begins to run out of power. But on a turbocharged engine, the critical altitude could be a lot higher. What is horsepower? Well, the horsepower developed inside the cylinders of an engine is known as indicated horsepower. But what's the horsepower delivered to the propeller of an aircraft? That is known as brake horsepower, the actual power delivered to the propeller. So inside the cylinders, indicated horsepower, delivered to the propeller, brake horsepower. All right, now here's a question. Does increased water vapor in the incoming air to a reciprocating engine increase or decrease the engine power at a constant RPM or manifold pressure? And the answer is increased water vapor decreases engine horsepower. And the reason for that is the water vapor is less dense than air, and it decreases the density of the air the engine's breathing, also displaces little oxygen. So increased water vapor normally results in decreased engine power at a constant RPM and manifold pressure. Now, we talked earlier about the concept of volumetric efficiency, and once again, volumetric efficiency is the ratio of the charge getting into the cylinder to the cylinder's displacement. When that piston goes down and leaves an area, that's the displacement, and it's how much charge you're getting in there compared to the displacement of that cylinder. And by the way, when they're talking about that charge, they're talking about standard pressure and temperature conditions, and so it's how many molecules really you're getting in there compared to what you would get under standard pressure and temperature. That's volumetric efficiency. Now, they're going to ask you on a test, what kind of things would decrease volumetric efficiency? What would cause it to go down? Well, part throttle operation would be one thing, because engines tend to operate more efficiently when they're running at lots of power. So part throttle operation would decrease volumetric efficiency. Also, we talked a lot about valve timing. Well, if you have improper valve timing, that'll decrease your volumetric efficiency. Also, if there's a sharp bend in the induction system of the engine, that'll actually impede the flow of air into the cylinder, and that will decrease volumetric efficiency. And high carburetor air temperatures means that the air going into the cylinder is less dense. Therefore, you're getting fewer molecules of charge into the cylinder, and your volumetric efficiency would go down. So these things all decrease volumetric efficiency. That's part throttle operation, improper valve timing, a sharp bend in the induction system, and high carburetor air temperatures. Now, let's assume that you're running, maybe you build an engine, you're running it. The question they're going to ask you on the test is, would it ever be possible to exceed 100% volumetric efficiency? Well, yeah, because it's based on standard conditions, and if you could somehow stuff the air into the cylinder, you could get more than 100% volumetric efficiency. How can you stuff the air in there? Well, you can do it by the use of a supercharger and actually stuff the air in the cylinder, and you get more than 100% volumetric efficiency. Now, let's assume you had a small induction system air leak, and that's going to have a very noticeable effect on the engine. When is it going to bother the engine the most, at high RPM or low RPMs? And the answer is the engine is having the hardest time when it's operating at low power, so a small induction system air leak will have the most noticeable effect on the engine at low RPM.
All right, let's you and I talk about these magnificent turbine engines. And these engines really are magnificent. Turbine engines have tremendous amounts of power. They operate remarkably smooth, and they're vibration-free. About the only thing you really say against a turbine engine is these things are enormously expensive. And I guess that's the way life goes. Anytime something is really, really nice, it's really, really expensive. And it's certainly that way with turbine engines. All right, let's you and I talk about how a turbine engine works. And to do that, let's take a look at a drawing of a turbine engine. And first of all, you have the air coming in the intake of the engine up here at the front. Then you have these rotating airfoils that compress the air as it goes through the engine. Notice, by the way, you have intake, now you have compression. So this compressed air now goes back into the engine, enters the burner cans, gets mixed with fuel, and burns. You have ignition, and then the burnt fuel air mixture expands and jets out the back and turns these rotating airfoils back, called turbines, and that creates the power to run the compressors. You have power, and then the air exhausts out the back. So notice you have those same 5 events taking place inside a turbine engine: intake, compression, power, and exhaust. Well, I should say intake, compression, ignition, power, and exhaust. Now, I got it right there. That's 5 events right there. All right, and what do the turbines do? Well, the whole purpose of the turbines is that the air jetting past the turbines rotates these airfoils of the turbines, and the turbines in turn rotate the compressors and make the compressors go. All right, now, those same 5 events occur in a turbine engine then that take place in a piston engine. In a turbine engine, they're called the Brayton cycle, and it's the constant pressure cycle. They don't ask you on a test, but on the piston engines, they're called the Otto cycle, and it's constant volume. But on a turbine engine, these same 5 events are called the Brayton cycle. You need to know that. It's a constant pressure cycle because the burner cans operate at a constant pressure. So that's the Brayton cycle, the constant pressure cycle. Now, we all know the principle in which a turbine engine works, particularly a fan jet. By the way, if an engine is a fan jet, if this compressor section is connected to a great big fan and some of the air bypasses the inner core of the engine, it's called a fan jet. If you don't have a fan up here at the front, it's called a turbojet. And a high bypass fan is one which has a lot of air bypassing the inner core of the engine. Now, we all know the principle upon which these kinds of turbines work is that for every action, there's an equal and opposite reaction. That's called Newton's third law. The air jets out the back, and that's the action which causes the engine to react in the opposite direction. That's Newton's third law. For every action, there's an equal and opposite reaction. Now, we all know that about jet engines. We know that's how it works. We know about Newton's third law. For every action, there's an equal and opposite reaction. Therefore, on the FAA written exam, they do not ask you about Newton's third law. They ask you about Newton's first law. And that's Newton's first law of motion. It's generally called the law of inertia. And it says that every body persists in a state of rest or motion in a straight line unless acted on by some outside force. That's Newton's first law, has nothing whatsoever to do with this, and that's why they ask you about that on the FAA written exam. So if they ask you about Newton's first law on the FAA written exam, do not get confused. Give them this answer. Newton's first law is every body persists in a state of rest or in motion in a straight line unless acted on by some outside force. How about that for something confusing? All right, now let's you and I talk about the 3 main sections of a turbojet engine. And they are the compressor, that's these rotating airfoils here at the front of the engine, combustion, which occurs in the burner cans, and the turbine section, which is these rotating airfoils that the air jets past and rotates to turn to compressors. So the 3 sections of a turbojet engine are compressor, that's up at the front, combustion, which is in the burner cans, and turbine. Those are the 3 sections of a jet engine. Now, for maintenance purposes, a turbine engine is divided into 2 basic sections. And that is the hot section, back here after fire takes place, and the cold section, which is before
fire takes place. By the way, the cold section can still be quite warm because you have a lot of compression taking place here, and compression heats up the air. But it's a lot cooler than after you inject fuel into it and start burning it, and then it gets very hot. Now, the cold section includes the engine inlet up here at the front, the compressor, and then very often after the compressor, you have a place where the space of the engine widens out, the duct widens out, and that's called the diffuser. Now, let's talk about Bernoulli's principle for just a second. If you remember, Bernoulli's principle says the faster a fluid goes, the more it expands and the less the pressure is on it. So if you have a narrow spot here, the air would rush through that and the pressure would be less. So if you get a wide spot in a duct like a jet engine, the pressure gets greater. The air slows down, the pressure gets greater, and that's what the diffuser is after the compressor blades. The engine, some engines tend to widen out here at this spot, and that's called the diffuser. Now that's the cold section. It's the intake, the compressor, and the diffuser. Now, the hot section of the engine includes the combustor, and that's the burner cans, the turbine, that's back here, and the exhaust section on the way back out. That's the hot sections of the engine. Now, another thing you should know about the operating principles of a jet engine is that jet engines operate all the time 80, 90% RPM. You can't really literally fly a jet engine operating at 50% power. And the reason for that is as engine RPM increases in a jet, the power increases exponentially. It increases tremendously. And the thrust you get out of the engine increases exponentially with small increases in RPM at higher RPMs. So the actual in-flight operating range of a jet engine tends to be 80% on up. And from 80%, we'll say, to 100%, the thrust will almost double. Between 80%, depends on the engine, but generally doubles between 80% and 100%. So jet engines at high RPMs, a little increase in RPM has a tremendous increase in thrust. So ask a question about that on a test. It says at higher engine speeds, thrust increases rapidly with very small increases in RPM. Now let's take a look at the factors that affect the thermal efficiency of a turbine engine. Now when we're talking about factors affecting the thermal efficiency, we're saying how much thrust you get out of this engine for the fuel that you put into it. Well, first of all, the turbine inlet temperature. If you could operate at very high turbine inlet temperatures, the engine actually becomes more efficient. Now, what happens is, what we're saying is, the hotter the air coming out of these burner cans and hitting these turbines, the more efficient this engine tends to be. Now, the problem is that you cannot use metals or cannot make metals that'll withstand the high temperatures that you'd like to have. So the primary limitation on the power and the efficiency of a jet engine or any turbine engine is the ability of these metals back here in the hot section to withstand the temperatures. So the biggest limitation on the thermal efficiency of a jet engine is that limitation of the metallurgy in the turbine inlet temperature area. Also, the higher compression ratio you have in a jet engine, the more thermal efficiency you have. So if you have the air coming in and keep increasing you can just add more and more stages of these airfoils and increase the temperature, the compression of the engine. And also, by the way, you do increase the temperature, but it becomes more efficient. So the higher compression ratio you can get, the more efficient the engine is. But once again, what happens is you get temperatures too high, the engine can't take it. And finally, turbine and compressor efficiency. If these airfoils back here in the turbine section are very well designed aerodynamically, it takes less power to turn them. Same way with the compressors. If these are efficient airfoils and efficient design here, you're going to get a lot more thrust out of the engine for fuel. Less thrust is spent turning the compressors. In other words, if you could get by without having to spend as much power to turn the compressors, the rest of it could be thrust. So what affects the thermal efficiency of an engine? Well, turbine inlet temperatures, compression ratio, and turbine and compressor efficiency. Now, let's take a look at the variables that affect inlet air density of a turbine engine. A turbine engine is really essentially a normally aspirated engine. And the more air you have coming in the front, the better the engine will do. So the speed of the aircraft affects the density of the air coming into it. Of course, the altitude of the aircraft, as you go to high altitudes, that engine is burning thinner air, and it doesn't do as well. And the ambient temperature, and jets are particularly affected very adversely by high temperatures. So if the temperatures are cooler, the jet does an awful lot better at cooler temperatures. So these are the things that affect the inlet air density of the engine, very much like a reciprocating engine, except the speed of the aircraft is much more of an important factor for a turbine engine than it is a reciprocating engine. Altitude of the aircraft and the ambient temperature. Now let's talk about how you measure thrust on a jet engine. And if the engine has a great big fan at the front of it like this, measuring thrust is pretty simple. All you have to do is measure the fan RPM somehow. And if you know the fan RPM, you'll know the thrust the engine's putting out, because that fan is just a great big pump pumping air. And if you happen to know the fan RPM, you'll know the thrust of the engine. But if the engine does not have a great big fan like that at the front of it, measuring the thrust is a lot more difficult. You can't use the fan, you have to use something else. Well, here is a very elegant solution to that problem. Let's assume you want to measure the thrust of this engine another way. What you could do is you put an air pressure gauge at the front of the engine, measure the air pressure going into the engine, put an air pressure gauge back here at the very back of the engine, at the exhaust outlet of the engine, and take the ratio of those two, and that would tell you thrust, and that ratio is referred to as engine pressure ratio. For short, they often call that EPR. And EPR is a direct indication of thrust output of the engine. It's the ratio between the exhaust gas pressure and the engine inlet air pressure, and it directly indicates the thrust produced by that engine. Now, on the test, they will say to you as a false answer, a distractor, they'll say EPR gives you an indication of volumetric efficiency. That is not correct. Volumetric efficiency, we already talked about, has to do with the piston engine. EPR is engine pressure ratio. It indicates thrust on a jet engine. It has nothing whatsoever to do, in this case, with piston engines. So it's a direct indication of thrust, and you get engine pressure ratio by dividing that turbine outlet pressure at the back by the engine inlet total pressure, and the ratio between the two is engine pressure ratio. And once again, it's a direct indication of gas turbine engine thrust. Now, we mentioned earlier that jet engines are greatly affected by high temperatures. You might wonder, well, how about high atmospheric humidity? Does that affect the jet engine very much? And the answer is no. High humidity has little or no effect on jet engines, so it's not a big deal in jet engines at all like it is in piston engines. Now let's talk about the various sections of a turbine engine, and let's lead off by talking about the compressor section. Actually, there's two types of compressors in a jet engine. Here's an example of a jet engine. It happens to be a JT15D, and this happens to have one that has an axial compressor right here at the front. Now, an axial compressor is a row of rotating airfoils. You can see right here a row of rotating airfoils that compresses the air along the axle or along the shaft of the engine. That's why they call it axial. It compresses the air by sending it back along the axle of the engine. Now, the other type of compressor, and the one we're going to spend most time talking about right now, is called a centrifugal compressor. So here's a centrifugal compressor, and let's take a closer look at the centrifugal compressor. Now, a centrifugal compressor works by taking the air, and it's basically an impeller, and it slings the air to the outside of the engine, and it compresses it that way. It's almost like a centrifugal pump. It just pumps the air, slings it to the outside, and compresses it. So there are actually two parts to a centrifugal compressor, and one part is the impeller, and you can see the impeller real well right here. And as I say, it just looks like a pump on a water pump, and it is just an impeller right there. And the other part to the centrifugal compressor is what is called the diffuser. We talked about that earlier. It's an area where the air goes into a wider chamber up here, slows the air down, and increases the pressure because it slows it down due to Bernoulli's principle. The slower a fluid goes, the more the pressure increases. So you have a diffuser here, which is just a wide area in the duct after the compressor that slows the air down and increases the pressure on it. So there are two parts to a centrifugal compressor. What are those two parts? Those two parts are the impeller and the diffuser. Okay, now, what is the advantage of a centrifugal flow compressor? Well, a centrifugal flow compressor normally can do the entire job in only one stage. Here you notice on other engines, we'll talk about it later on, there's rows and rows and rows of axial compressors. But on a centrifugal compressor engine, you may have only one or two stages, and that is because there's a very high pressure rise per stage in a centrifugal compressor. Now, there are also two types of centrifugal compressors. This is a single entry compressor. In other words, there's only an impeller on one side, but there are double entry compressors that are centrifugal compressors, and they work by having another impeller identical to it on the other side. Air comes around, enters from the other side, and you use both sides of this disc,
and put impellers on them and centrifuge the air out with an impeller on both sides. So if you have an impeller on both sides, that's called a double entry centrifugal compressor. This happens to be a single entry centrifugal compressor here. But a double entry centrifugal compressor has vanes on both sides of the impeller. Now, that's enough for centrifugal compressors. Let's you and I take a look at an axial flow compressor. Now, an axial flow compressor is one that has rows and rows and rows of rotating airfoils. And the advantage of an axial flow compressor is it's very efficient, high peak efficiency, and you can get a greater pressure ratio. All you have to do is add more and more of these rows of airfoils. Now, let's you and I take a close look at an axial compressor. So here's an axial compressor. Now, it's very important that the air striking these compressor blades comes in at the right angle. So in order to ensure that the air does come to the axial compressor at the right angle, sometimes you have what is known as an inlet guide vane assembly. And here's an example of an inlet guide vane assembly. By the way, it's cut away up here. So you can look down here. And the inlet guide vane assembly is an assembly that directs the air so that it strikes the compressor blades at the proper angle. On the test, you need to know the function of the inlet guide vane assembly, and that's this right here on an axial flow compressor, is to direct the air into the first stage rotor blades at the proper angle. Now, let's take a look at the engine from a bigger scale again. Now, if you look real close at an axial compressor, you'll notice that in between the rows of rotating airfoils, there's also stationary airfoils in between. Now, they've cut them out, but you'll see down here there's stationary airfoils in between the rows of rotating airfoils. Well, the rotating airfoils are called rotors, and the stationary airfoils are called stators. Of course, the rotating airfoils are designed to move the air back, and the stators are designed to direct the air and shape it to meet the next row of rotating airfoils. So the two parts that are basic parts to a centrifugal compressor are rotors, and they rotate, and stators, and they stay stationary. That's why they call them that. So it's made up of a series of rotating airfoils, that's an axial compressor, and stationary airfoils. Now, once again, the stationary airfoils are called stator vanes. Each row is called a stage. Each one of these series, one rotating section called a rotor and one stationary section called a stator is called a stage. And so what do the stators do? As I said earlier, they help guide the air going into, and they also act to diffuse the air. So that's, again, slow it down and increase the pressure. And so these stators, once again, do a diffusing effect as well. That's slowing it down, increasing the pressure. All right, what are they called? Well, the combined, a rotor and stator combination is called a stage. And once again, those stators act as diffusers to decrease the velocity of the gas and then increases the pressure, and it prevents swirling, and it controls the direction of the airflow. They're kind of like guide vanes. Stators do exactly the same thing. They guide this air around and slow it down and increase the pressure as a result of it. And the idea of that then is the stator converts velocity energy into pressure energy, and it does it the same way a diffuser does, slowing it down, decreases the velocity, increases the pressure. Once again, they're all called stages, and all you have to do is to increase the pressure ratio of this engine is to have more and more stages. So as you go along here, you increase the pressure ratio, you just add more and more stages. Now, we're talking about pressure ratio, we're talking about how much the compression ratio of this engine is. So what's the primary factor, they ask you on the test, which controls the pressure ratio or compression ratio of a turbine engine? And the answer is, if it's an axial engine, it's a number of stages in the compressor. Now let's take a look at the entire drawing of a jet engine again. And the thing I want to point out about this particular engine is that there's two rotors. There's the orange-colored rotor in the inner part, and we're going to call that N2, by the way. And there's a blue-colored rotor that's the outer part of the engine. We're going to call that N1. Now, this N2 rotor then has the air immediately after the burner cans that turns this turbine. And since the air is right after the burner cans, that's high-pressure air, and that's called the high-pressure turbine. Also, you notice that the N2 compressors would also be called the high-pressure compressors. And the reason for that is the air is boosted up, the pressure is boosted up a little bit by these compressors up here, and then these are the high-pressure compressors that boost it up even further. So you have this shaft and this turbine and this compressor, and that's called N2, and that's the high-pressure turbine and the high-pressure compressor, and that's N2.
And all the way inside this shaft, there's another shaft that would be blue in color in our little drawing here, and it goes to the low pressure turbines. And the reason this, or low pressure turbines, since there's two of them there, and the reason they're low pressure is some of the air pressure has already been extracted by the high pressure turbines. So these are low pressure turbines, and this is a low pressure compressor because it's the first compressor is just beginning to compress the air. And that shaft goes inside the N2 shaft, and this is called N1. Now this has a lot of advantages to it. First of all, if you're going to start an engine like this, all you have to do is get into rotating. And you get into rotating, and these compressors compress the air, you put fuel to it, and then the whole thing will light off, and then when the air starts jetting out the back, it'll also start rotating N1. But to start this engine, you don't have to turn over the entire engine. All you do is turn over N2, and this engine's a little easier to start. Also, you'll find that these two rotors will rotate at different speeds. So as you go to higher altitudes, N1 seeks its own speed. There's thinner air at higher altitudes, so this N1 compressor might speed up a little bit in the thinner air, and N2 would seek its own speed, and that means each turbine and each compressor, turbine compressor, or each rotor actually, is operating most efficiently. Now you see this on turbojet engines and sometimes turbofan engines, and also on what they call high volume turboprops. That means turboprops that really move a high volume of air through them will have what they call two-spool or split compressors. And once again, when they're operated at high altitudes, the low pressure rotor, and that's N1, will increase in speed as the compressor load decreases in the thinner air at high altitudes. And that lets this thing, the N1, seek its own speed. So the way they put this on the test is a low pressure compressor in a turbine engine with a dual axial compressor seeks its own best operating speed. Now, what are the advantages? Well, split spool, axial flow compressors. Axial flow, remember, are the ones that move the air back along the axle instead of centrifugal. So split spool, that's what this is, split spool, axial flow compressors offer the greatest advantages for both starting flexibility and improved high altitude performance. Those are the things you need to know about that on the test. They also call it a dual axial flow compressor, split spool or dual axial flow compressor, and it improves the efficiency of a turbojet engine because you have higher compression ratios. Why? Because you simply have more stages of compression. All right, now they're going to ask you some more questions about it. How about the fan rotational speed of a dual axial compressor forward fan engine is the same as the low pressure compressor? Let me translate that into English. That was an FAA test question. I'll translate it in English. What they're saying is if you have a fan on this engine, it's attached to the low spool compressor, so it operates at the same speed. So let me read it one more time. The fan rotational speed of a dual axial compressor forward fan engine, they're saying the fan speed of this engine is the same as the low pressure compressor because they're attached to each other, that's all. What determines the compression ratio then of an axial flow compressor? And the answer is the number of stages. We've already covered that. And where will the highest gas pressure in this engine occur? Now that's almost a trick question. You would think offhand that the highest gas pressure would occur in a burner can, but that is not true. The highest gas pressure, air pressure, the highest pressure in a jet engine occurs as you come out of the last compressor stage, or as you end the diffuser here, if there's a diffuser here, or as you enter the burner can. Those are all three about the same place. Out of the compressor outlet, in the diffuser, or at the entry of the burner can. Why not in the burner can? Well, the purpose of the burner can design, the aerodynamic design, is to increase the velocity of the air. The air coming out of the burner is at high velocity, and it's not at the highest pressure. The highest pressure is that as the air enters the burner can. If you have to think about it, it has to be that way, because if you didn't have higher pressure outside the burner can, the air would not enter the burner can. So the highest pressure is on the entrance to the burner can. Now let's take a look at the design of a turbine engine compressor blade. And I want you to know that sometimes a compressor blade is known as a cutout, meaning it has a hole in it and it reduces blade tip thickness. So just as a question on the FAA written exam, the profile of a turbine engine compressor blade is a cutout that reduces blade tip thickness. That's what you needed to know. Now let's take a close look at an axial flow compressor in a turbine engine. And when you do that, you'll notice these compressor blades are airfoils just like the wings on an airplane. And just like the wings on an airplane, they can stall, particularly when the engine's going at low RPM, there's not much ram air pressure. These compressor blades are working pretty hard and they might stall. There is a solution to that, and what you can do is relieve some of the pressure from these compressor blades by venting off some of the excess air within the compressor and venting it overboard, and they use bleed valves to do that. So, here's what the FAA wants you to know about this. The bleed valves are used to vent excess air within the compressor section to allow the air to go overboard. And that's particularly a problem that prevents compressor stall when you have low compressor RPMs and low ram air pressure coming into the engine. Now let's you and I take a look at our drawing of a jet engine again. We'll take a look at the diffuser section. We talked about it earlier. First of all, where is the diffuser section located? If you remember, it's kind of a wide spot in the duct after the compressors and before the burner can. So the diffuser section is located between the compressor section and the burner section. What is the purpose of the diffuser section? Well, remember Bernoulli's law says if you slow a fluid down, you increase the pressure. So the purpose of the diffuser section in a turbine engine is to increase pressure and reduce velocity. They're going to ask you, where is the pressure the greatest in a jet engine? Once again, it's the compressor outlet or the diffuser section has the greatest pressures. After the diffuser section, you have the combustion section. And where is the combustion section? Well, we've shown it right here, these beautiful burner cans right here, and that provides for proper mixing of the fuel and air. And the air passing through the combustion chamber of a jet engine is used to support combustion and also cool the engine because there is more air going through the burner cans than is necessary for combustion. The rest of it is to cool the engine. And they're going to ask you, where is the highest gas pressure in a turbojet engine? We already covered that. Just as you leave the compressor or enter the diffuser as you're in the diffuser, or at the entrance to the burner cans. All means the same thing essentially. The highest gas pressure is just before the burner cans. You could call that the diffuser section, you could call it the inlet to the burner cans, or you could call it the outlet to the compressor, but it's all the same place. Now, the thing about a gas turbine engine is that combustion occurs at a constant pressure. So here in the burner cans, the combustion occurs at a constant pressure, and that's why they call it a Brayton cycle or a constant pressure cycle that the turbine engine operates on. They're going to ask you, what are the types of combustion sections found in aircraft turbine engines? Well, we have examples right here of multiple cans. That's just little individual cans. Now, an annular section is like a donut. It's an entire donut going around the rotor here, and that's an annular section. The word annular means donut. Why they don't call it a donut section, I don't know. Another type is can annulars, cans arranged in donut fashion around the rotors. So the three types of burner cans or combustion sections are multiple can, annular, and can annular. Now let's move beyond the combustion section and go back to the turbine section back here. And the turbines, as you remember, are these rotating airfoils. The air coming out of the burner can turns these turbines. And turbines also have rotors and stators. The rotors are the rotating airfoils, the stationary airfoils that you can't see really in this cutout very well, but they're there. Stationary airfoils that guide the air into the turbines are called stators. So the purpose of the stators is to, in this case, increase turbine velocity. Let's take a look, or increase air velocity. Let's take a look at it. In this case, you'll notice the stators are arranged so that they get narrower, and then the air has to go through here faster. And so what happens is that the stators increase the velocity. These are the stationary airfoils, and these are the rotor parts, the moving airfoils, and the stators increase the velocity of the air as it goes to the turbines. Now the stators in the compressor section actually decrease the velocity of the air, so they're different. Here these stators are designed so that they get narrower and increase the velocity of the air. Now they call these stators sometimes, just before the turbines, they call that a nozzle diaphragm. And all it is a row of stators. And they call it a nozzle because if you look at these stators, they look like they squeeze the air down like a nozzle does right here at this particular point. So they're going to ask you, what is the function of a nozzle diaphragm in a turbojet engine? And the function is to direct the flow of gases to strike these turbine buckets. These turbine blades are often called turbine buckets at a desired angle. Now, there are basically two types of turbine blades or turbine buckets, and there are two types of reaction and impulse. Now, if you look at this, the air hitting this would move this turbine blade just like water moves a water wheel. Well, that is called an impulse type of turbine blade. If the air moves it just like water moves a water wheel, you'd call that an impulse blade. If, on the other hand, the airfoil shape of the turbine blade makes it move, that is called a reaction type. And actually, turbine blades can very often be both at once. One section of the turbine blade is an impulse blade, and another section of it is a reaction section, and the two combined are reaction impulse blades. But those are the two principles that turbine buckets or blades work on. That's reaction and impulse. Now, sometimes they put a shroud over the ends of these turbine blades, like so. You'll see a shroud over the ends of them, and just completely connect them together. And they're shaped, that shroud would be shaped so that the ends form a band or a shroud, and that reduces vibration and improves airflow characteristics. So they're going to ask you, what do shrouded turbine blades do? Well, they improve airflow characteristics and they reduce vibration. That's the purpose of shrouded turbine blades. They're also going to ask you, what's the most satisfactory method of attaching turbine blades to the turbine wheels? And the answer is the fir tree design, and you are seeing a great example of a fir tree design right there. Now, let you and I take a look once again at this centrifugal compressor, and here's a good example of a centrifugal compressor. They're going to ask you a question on the test. How do you join the turbine shaft, here's the turbine shaft, and here's a turbine back here on the right, to the rotor of a centrifugal compressor? How are these two joined together? And the answer is with a spine coupling, very much like the drive shaft on a car going out of the transmission into the drive shaft has a spine coupling, and that's how those two are held together with a spine coupling right there. Now, let you and I take a look at our drawing of a jet engine again. They're going to ask you a question on the test. They're going to say, take a look back here, and you see that there are two turbines attached to the same shaft, two turbine wheels having a single shaft. Why would you have more than one turbine wheel on the same shaft? And the answer is to extract more power from the exhaust gases than you could with a single wheel. That's that simple right there. They're also going to say, take a look at these turbines near the rear of a jet engine back here. What is their purpose? Why are they on this engine? And the answer is the function of these turbines near the back of a jet engine is to drive the compressors up at the front of the jet engine, and that's the only reason they're there. They're going to say which turbine drives the N2 compressor. All right, now if you remember, N1 is the compressor at the very front of the engine. It's driven by the turbines at the very back of the engine. That's N1, from the very front of the engine to the back of the engine. This is the low pressure compressor, and this is the low pressure turbines. N2 is the high pressure compressor and the high pressure turbines. So if they ask you which turbine drives the N2 compressor, it's the first stage turbine or the high pressure turbine. This is a first stage turbine, this is a second stage turbine. So this first stage turbine drives the N2 compressor. They're going to ask you that on the test. They'll also ask you a few things about terminology. Let's take a look at what they're going to ask you about terminology. They're going to say, what does PT7? Well, PT stands for total pressure. That's total pressure at station or position 7 in the jet engine. They're going to ask you, where is position 7 here? Well, position 7 on a two-spool axial flow compressor is at the very rear of the engine, right here at the outlet of the engine, and it's the turbine discharge pressure. And so the abbreviation PT7 means total pressure at station 7. And where is station 7? It's total discharge pressure, identified in the service manuals, they say, as PT7, and it's right here at the back of the turbine engine, PT7 back there. We talked about it earlier. What is the ultimate limiting factor of a turbojet engine? And the answer is turbine inlet temperature. That's the ultimate limiting factor, because if you could withstand higher temperatures, you could get more power and more thermal efficiency out of the engine. Enough with the turbines. Now let's go out to the very back of the engine, and you and I talk about the exhaust section of a turbine engine. What is the purpose of an exhaust section of a turbine engine? Well, it's the primary function of it's to straighten and collect exhaust gases into a solid, high-velocity exhaust jet. Now, how do you straighten them? Well, the reason you straighten them is that you don't want them swirling around, and if you look, there's a cone here in the inner part of the engine. It's normally held by little struts, and those struts help to straighten the velocity, straighten the air. So
The exhaust jet at the back, the primary function of the exhaust cone is to straighten and collect exhaust gases into a solid, high-velocity exhaust jet. The exhaust section of a turbine engine then imparts a high exit velocity to the exhaust gases, something you need to know. And it's located, where is the jet nozzle on a turbine engine located? Well, it's located at the exhaust section of a turbojet engine. Now let's take a look at a couple designs of exhaust sections of an engine. And first of all, here is a convergent nozzle. Well, the nozzle comes in and tightens up here at this particular point, restricts the space that the air has to flow through. And a convergent nozzle, and we're talking subsonic air now, causes subsonic air to increase in velocity. And Bernoulli's law says when something increases in velocity of fluid, what happens to the pressure? It decreases the pressure. So a convergent nozzle causes the air to increase in velocity and decrease in pressure. Now let's talk about what, and when you're talking about subsonic air, a divergent nozzle would do. Well, a divergent nozzle, and this is, by the way, an example of a divergent nozzle, because if you look at this cone here, and if you look also at this outer part of the nozzle, the space for the air gets greater instead of less. See how it gets greater there? That's a divergent nozzle, and that causes the pressure to increase and the velocity of the air to decrease. Again, it's Bernoulli's law. Now, unfortunately, Bernoulli's law kind of goes out the window when you're talking about supersonic air. We'll talk more about that later on. But let's talk about one more time. Convergent air causes at the nozzle, causes the velocity of the air to speed up. Convergent nozzle causes the velocity of the air to speed up and the pressure to decrease. A divergent nozzle then causes the air to slow down and the pressure to increase. So what does an exhaust cone do at the aft part of a jet engine? Well, this is an exhaust cone, the whole assembly like this, and it'll cause the pressure to increase and the velocity to decrease if it is divergent, Now, the last thing we need to talk about is supersonic flow of the air. And if you have supersonic air, we're talking a whole different ball game. And if you have there are very often when they're talking about supersonic air, you're talking about an engine that goes supersonic. An afterburner has supersonic air very often through it. An afterburner very often has a convergent nozzle and a divergent nozzle. And if you have a divergent nozzle and supersonic flow, and you have to memorize this because this is different than Bernoulli's law would say, a divergent nozzle with supersonic flow causes the air to decrease in pressure and increase in velocity, and that's with supersonic flow. Believe it or not, we have discussed everything you need to know on the FAA written exam about turbine engine and reciprocation engine theory and construction.